Now we will have another phenomenon of the wave called as polarization. So before going to the types of polarization, just we will discuss what is polarization. Here what do you mean by polarization? It's a simple understanding word that used for replacing polarization is nothing but orientation. Here what we are discussing is about the orientation of the wave. So clearly observe or imagine, so wave is travelling in space which is of sinusoidal nature. So when it is a sinusoidal nature, always we will think that the sinusoidal wave may be like this. It is travelling towards or outwards the plane of paper from my side to your side. But if the wave is travelling like this, then this is also the sinusoidal signal which is travelling from my side to the your side, but it has a little bit angle with respect to the x-axis that what we have, or a horizontal plane what we have. That simple orientation is called as nothing but polarization. So now clearly what is the definition of the polarization? Here the path of the tip which was followed by path of the tip of electric field, it is not magnetic field, clearly we are taking only electric field. The path of the tip of our electric field when we are observing it from one end of the wave path. That here we are observing how the tip of the electromagnetic wave or the simple electric wave is varying when we are observing it from the one end. If you are observing from your side or my side, if it looks like a straight line, then it is said to be a linear polarization. If it looks like some elliptical nature, it is said to be the elliptical polarization. If it looks like a circle, then it is said to be a circular polarization. That simply it is a locus point of the tip of our electric field, nothing more than that. Now imagine, let us take the electric field is travelling in z direction. Since it is travelling in z direction, the component may be in either x direction or y direction. That's x direction or y direction. If it is having only x component, that the electric field will travel like this. That is, only x component of the electric field will be there, it is travelling in z direction. If you are observing that particular wave from your side, then simply it is seen like a straight line, nothing more than that, right? In the same way, if the electric field has only y component, there is no x component, only y component, then the electric field will travels like this. If it is travelling like this from your side or my side, if I observe that one, it looks like just a straight line, that the tip of our electric field will move like a straight line. So this is said to be a linear polarization. Like that we have different types of polarizations. Now one by one we will discuss about all those types of polarizations. To discuss about all those types of polarizations, we require the components of the electric field. We are not considering any magnetic field, just we are considering the magnetic field, and with the help of examples you can easily understand what is the type of polarization which can be observed for different cases. For that, what I am assuming is the wave is propagating in z direction. If the wave is propagating in z direction for a linear, homogeneous and a plane wave, that what we have is x component and y component. That I am assuming two equations for x component and y component initially, and I will apply different amplitudes and different phases between those two waves, then I will observe what is the resultant, right? So clearly consider this one as case by case. Initially what I do is I will take xy plane, that is, since I have only two components, I will take the xy plane and I will try to draw the resultant of that one, right? So first what I do is I will consider the general equations for x electric field and y electric field. Let us take Ex of z. Here clearly the wave is travelling in z direction and x component we have here. So Ex of z is equals to some amplitude E01 I am considering, and let us take the general equation is cos omega t. That here what I am doing is, for our convenience I am suppressing the remaining all terms what we have in our general wave equation. Just I will consider E01 cos omega t, since the wave is a function of time, that what we require. I am considering this E01 into cos omega t. Since it is in x direction, just to take x as the additional unit vector which supports the wave equation. In the same way, the component of electric field in y direction, that is Ey of z is equals to, I am considering another amplitude E02. So initial amplitude E02 multiplied with same type of wave omega t plus or minus phi ay, that I am adding some phase difference. We don't know how much phase difference we can be observed between x and y. Later for special cases we will apply it. That phi will be substituted with different values, right? Case by case we will observe what happens if I am varying these two? What happens if I am varying this phi? We require, once again remember, we require the resultant of Ex and Ey, right? The resultant of Ex and Ey is nothing but the electric field that what we have, right? I will consider case 1. Let the amplitudes are same, that let us take E01 is equals to E02, and the phase difference between these two is 0. Just what I am doing is, initially I am considering there is no phase difference between them and the amplitude is same. So I am taking E01 is equals to E02 and phi is equals to 0. Then write down the equation of Ex of z and Ey of z. Simply Ex of z is equals to, just it is E01 cos omega t Ax. And what is Ey of z? Ey of z is equals to E01. Since E01 is equals to E02, I am writing E01 here. Cos omega t Ay. Now for some time and for our understanding, ignore the vectors, just consider the magnitudes. At every instant of time, observe Ex of z is equals to E01 cos omega t. Every instant of time, Ey of z is also equals to E01 into cos omega t. So whatever may be the amplitude we will get for Ex of z, the same amplitude we will get for Ey of z also. So if you draw the graph between Ex of z and Ey of z by considering them on two axes like this, let us take this is Ex of z and this is Ey of z. So by varying time, at every instant of time we are getting the same amplitude, right? So if you draw the graph will be like this, a simple straight line, that what we get. So when you are observing from one end, that is you are at some location, right? When you are observing from one end, by varying the time, if you draw the graph, obviously this will be a straight line. Then it is said to be linearly polarized signal. Nothing more than that. That the resultant of the electric field that what we are observing is a clearly linearly polarized signal. Then what will be the angle between them? That angle will be calculated with respect to the x-axis. Simply it is theta. Already we know what is the formula for calculation of theta. So theta is equals to tan inverse of Ey divided by Ex. Since these two are same in this particular case, which is equals to 45 degrees. So if we are considering a simple generalized statement for this particular case, can be tell like this. If we are considering same amplitude and same phase for the components of x and y, what we get is a 45 degrees oriented signal, and clearly it is a linearly polarized signal. So when you are observing that from one end, what we get is a simple straight line. So this is a simple case. Clearly remember, a linearly polarized signal with orientation angle 45 or polarization angle 45 degrees. Now what I do is I will consider the second case. In that second case, I will consider once again the same phase, that the phase difference is 0, but I will vary the amplitude. If I vary the amplitude, what happens? Just observe as case 2. So in this case, I am considering two different amplitudes, that is E01 is not equals to E02, but the phase difference between these two is 0, right? Now write down the equation of x, that Ex of z is equals to E01 multiplied with cos omega t Ax. Write down equation of Ey of z is equals to E0 t same, so E02 cos omega t Ay. Now here clearly, since E01 and E02 are not same, I am writing E01 and E02 in the original expressions as it is, but we may have some relation, that E01 is equals to some k times of E02 like that, right? Now try to get the relation between these two, that what we have is Ex of z divided by E01 is equals to Ey of z divided by E02. Therefore, so Ey of z is equals to E02 divided by E01 multiplied with Ex of z. Once again clearly observe what is the equation we got. The equation what we got is simply in the form of y is equals to mx. that now this particular equation has some slope, that the slope is equals to some m is nothing but E naught 2 by E naught 1. So if you draw the graph between these two again, that's Ex of z and Ey of z, that is nothing but the resultant of our electric field. Once again we will get a straight line like this. So this is the x, on x axis what we have is Ex of z, on y axis what we have is Ey of z. So if you draw the graph between these two, that the graph may be a straight line, so which follows through the origin. So that may be like this. Once again it is a straight line, but the polarization angle may not be 45 degrees. So clearly once again what we can observe is the two equations have different amplitude but zero phase difference will gives us a linearly polarized signal. Now once again, what is the polarization angle? Polarization angle theta is equals to tan inverse of Ey divided by Ex. So this polarization angle, that what we will get using this simple expression. So till now just we observed two cases. In those two cases we got only linearly polarized signal, that is the resultant of our x and y. So the resultant of our x and y always a straight line. In the first case we got exactly with 45 degrees angle, but in the second case we don't know what is the angle, but with this equation we can calculate that particular angle. Now this is simply a linearly polarized signal when we have both x and y. If we have only x, then the electric field will be obviously in the direction of x. If Ey of z is equals to 0, then the total electric field will be in the direction of x only. Then it is said to be horizontally polarized signal. Just identify these names and remember them. So if y is equals to 0, the total field will be travelled in the direction of x only, but the resultant is just like a straight line. If you are observing that one from one end, it's just like a straight line, right? So it is said to be the horizontally polarized signal. In the similar way, if x is equals to 0, only y exists, then the wave will looks like a straight line which is in vertical direction. Then it is said to be vertically polarized signal. So clearly vertically polarized signal, horizontally polarized signal, and the signal with some other polarized angle. These three will comes into the linear polarization category. That for the linear polarization category, the condition must be clearly the phase difference must be 0 and amplitude may be anything. So we have varied the amplitude and we got the same linearly polarized signal, but the phase difference must be 0. Now if the phase difference is some other thing, then what happens to it? We will observe that one as case 3. So now in this case what we do is we will consider a special phase difference between those two, a specific case, that pi by 2 I will take with different amplitudes. So here in this case what I am doing is a phase difference phi is equals to pi by 2, that take phi equals to pi by 2, and the amplitudes are same as it is the previous one, that is E01 is not equals to E02. Then try to obtain the equivalent equations. Then Ex of z is equals to, what is Ex of z in this case? As it is, the original one is E01 cos omega t Ax, and what is Ey of z? So Ey of z is equals to, so E02 as it is amplitude I am getting, and so here what I am doing is instead of this phi I will substitute pi by 2. So this can be written as cos omega t plus or minus pi by 2 Ay. But here in this case we will get two more sub cases can be observed. That is, what happens if it is plus pi by 2, what happens if it is minus pi by 2. That what I do is just individually I will explain. So consider Ex of z again as the same equation I am writing, which is equals to E01 cos omega t Ax, and initially I will consider plus pi by 2 here. So if I consider plus pi by 2, this can be written as E02 cos omega t plus pi by 2 Ay. So what is cos omega t plus pi by 2? Obviously it is minus sine minus E02 sin omega t Ay. So these are the equations that what we are supposed to take if phi is equals to plus pi by 2, right? In the same way I will consider minus pi by 2 also. By considering minus pi by 2 here, I will write down the equations once again. That is Ex of z is equals to E01 cos omega t Ax. if I take minus pi by 2, cos omega t minus pi by 2 is sin pi by 2, it is plus sin pi by 2. Therefore, Ey of z is equals to E naught 2 plus sin omega t Ay. So, clearly remember this is for plus pi by 2 case and this is for minus pi by 2 case. Now, once again observe the resultant. Resultant is nothing but the equivalent of Ex and Ey. Here also the resultant we require. That is what we get for Ex and Ey. Just observe Ex of z is equals to E naught 1 cos omega t. I am neglecting the vector for some time. Here also I will neglect the vector for some time. Ey of z is equals to minus E naught 2 sin omega t Ay. Get cos omega t from this one, get sin omega t from this one, square and add them. Once again, get cos omega t from this equation, get sin omega t from this equation, square them, add them. So, cos square omega t plus sin square omega t, which is equals to 1. Here also, get cos omega t from this equation, get sin omega t from this equation, square and add them. Cos square omega t plus sin square omega t, which is equals to 1. So, directly I am writing the equivalent equations here, that cos square omega t plus sin square omega t, that Ex of z divided by E naught 1 whole square, that is nothing but cos square omega t, plus sin square omega t, that is Ey of z divided by minus E naught 2 whole square. Cos square omega t plus sin square omega t is equals to 1. That is the equation that what we got for this particular case. Similarly, obtain here cos square omega t Ex of z by E naught 1 whole square plus sin square omega t Ey of z by E naught 2 whole square, which must be equals to 1. Since it is in a square term, this negative term also becomes positive, right? So, this is x by a whole square plus y by b whole square is equals to 1. X by a whole square plus y by b whole square is equals to 1. So, in those two cases, that is for plus pi by 2 case and minus pi by 2 case, just what we are getting is same expression as the resultant, right? Now, clearly recollect the mathematical of basic equations. This particular equation always resembles an ellipse equation. This equation is nothing but the similar one, represents an ellipse equation. So, clearly what you can understand from this particular case, if you have different amplitudes and phase shift is exclusively pi by 2, then we are getting an elliptical shape when you are observing it from the one end. So, this is said to be elliptically polarized signal. But in that elliptically polarized signal also, so how to differentiate this case and this case? So, what is the name for this particular case and what is the name for this particular case? Here clearly observe, this Ex of z is equals to E naught 1 cos omega t, Ey of z is equals to minus E naught 2 sin omega t. Clearly this Ex lags Ey here. Here this Ex leads Ey here. So, in one case Ex is lagging, in another case Ex is leading. So, what happens when Ex is lagging, what happens when Ex is leading? For that, just a small understanding is required. Here what we are doing is we are observing the wave with respect to the time. So, what you do is just vary the time from 0 to some value. Here for our understanding, what I am doing is in the first case I am varying time, that t is varying from 0 to omega t. That what I do is I will take 0 as one value, I will observe the components or the resultant, and the final value is omega t, I will observe the components, right? And I will try to draw the graph between them. So, if time t is equals to 0, if time t is equals to 0, what is Ex of z? Substitute t is equals to 0 here, cos omega t is just 1. So, Ex of z is equals to E naught 1. So, at time t is equals to 0, I am writing this one. Ex of z is equals to E naught 1, and what is Ey of z? Ey of z is equals to, since what we have is a sinusoidal term, directly what we get is 0. So, clearly observe, initially at time t is equals to 0, among these two components only x component we have, there is no y component. So, if you want to represent that one as a graph, only on the x axis you have to put a point. So remember that one, later I will draw you the graph, no problem. Okay, so at a time t is equals to 0, initially only on x-axis we have the electric field. In the same way, the final time what I am considering is omega t. It's not omega t, sorry for that. Just instead of this omega t, consider pi by 2. So time t to 0 to pi by 2, that what we are considering. So omega t is equals to pi by 2, I am substituting as the second one, right? That is the final time. So if I substitute pi by 2, what is x component, that is Ex of z is equals to Ex of z, instead of omega t I am writing pi by 2, cos pi by 2 is 0. So simply Ex of z is equals to 0, that what I am getting. The same time I am substituting in Ey of z also. If you substitute omega t is equals to pi by 2, so Ey of z is equals to minus Ey of z is equals to minus E naught. So just observe what I am doing. Nothing, I am taking two times, the initial time 0, final time pi by 2. Initially I am substituting 0 in this in these two expressions, I am getting this condition, and final time, it's a pi by 2 I am substituting instead of omega t, I am getting this condition. So initially where is our vector field component? The field component is along x-axis. Later at the final time, where is our field component? It is on negative x-axis. That Ey of z is equals to minus E naught 2, that what we got, minus E naught 2 means it is on negative y-axis. So if you draw the graph between x and y, simply it looks like this. So let us take, this is our Ex and Ey, on the negative side it is minus Ey, right. Initially at the time t is equals to 0, this is at the time t is equals to 0, Ex of z is equals to E naught, Ex of z is equals to somewhere it is E naught 1, that what we have amplitude, right. There is no Ey of z at time t is equals to 0, so no need to represent it. Now the time is going on, the time is going on, that we are substituting omega t is equals to pi by 2. At some time omega t is equals to pi by 2. What is the electric field? The electric field is only on Ey, that is also with negative value, that is somewhere here minus E naught 2 we are supposed to represent. So clearly as the time is going on, the vector is moving from x to negative y axis like this with elliptical shape. Don't take this one as a circular shape, with elliptical shape, right. So in which direction it is moving? Clearly from x to negative y. So if it is taking a rotation like this, then it is from y to x, right. So the rotation is taken from y to x. This is clearly a left-handed coordinate system. So always remember that whenever we are taking a general rotation from x to y, y to z, z to x, then it is said to be the right-handed. But here the rotation is taken from y to x. Since it is from y to x, it is said to be a left-handed elliptically polarized signal. So clearly identify what I am doing. Once again, it is very easy if you can understand that I am taking the initial time and I am taking the vector, resultant vector, that resultant vector is along x. I am taking the final time, the resultant vector is negative y. So clearly between these two, obviously the vector will move from x to minus y, that is nothing but y to x, that it is taking a clockwise rotation. So if we are taking a clockwise rotation or a left-handed coordinate rotation, then it is said to be left-handed elliptically polarized signal. So what is the condition for that left-handed elliptically polarized signal? So once again recollect, the amplitudes must be different, the phase difference must be plus pi by 2 only, right. So in another way, the Ex lags Ey. So in the examination, whatever may be the point you are observing, directly you can say that it is a left-handed elliptically polarized signal. In the similar fashion, observe the second one. For the minus pi by 2 case, just what we do is we will observe by considering two different time slots. Let us take at a time t is equals to 0. At a time t is equals to 0, what is Ex of z? If you are substituting time t is equals to 0, this Ex of z is equals to zest E naught 1. That what I am doing is only considering magnitude, right. At the same time, at a time t is equals to 0, what is Ey of z? Ey of z is equals to, since it is 0, the entire quantity is 0, right. So at the initial time, Ex of z is equals to E naught 1 and Ey of z is equals to 0. And I am taking a different time, a positive time, that is the time moves on, that at a time t is equals to or omega t is equals to pi by 2. Here also this is omega t you can consider. Say at omega t is equals to pi by 2. So what is this Ex of z? Ex of z is equals to this E naught 1 into, since it is pi by 2 term, simply what we get is 0. Right? In the same way, if you substitute omega t is equals to pi by 2 here, Ey of z is equals to just plus E02. That what we are getting is a amplitude term. So initially the electric field is along x-axis only, right? After some time, that is at time t is equals to pi by 2, the electric field is along y-axis only, that is clearly it's a positive y-axis. And try to draw the graph that at a time t is equals to 0, the electric field along x-axis, that what we have. After some time, the electric field is along y-axis, that what we have. So in between these two, what happens? Clearly the electric field is moving from x to y. Since it is moving from x to y, we can say that it is a right-handed polarized signal. Clearly it is a right-handed elliptically polarized signal, that what we have as an exclusive case. Right. So clearly remember, if it is taking a rotation in clockwise or if it is taking rotation from y to x, then it is said to be left-handed coordinate system, left-handed elliptically polarized signal. For that, the condition is Ex lags Ey. Clearly we can observe the equations here. In the same way, if Ex leads Ey, the rotation is always from x to y or anti-clockwise rotation, then it is said to be right-handed elliptical polarized signal. So in the elliptical polarization, these two are the two subcategories. For that, clearly we have separate conditions, the amplitude is different, but the phase shift may be either plus pi by 2 or minus pi by 2. So this is one of the cases that what we are discussing. As the last case, we can discuss about, so another one, if the amplitudes are also same, as the phase difference is plus or minus pi by 2 and the amplitudes are same, what happens to that? We will discuss now. As the last case, what I am doing is I am taking the phase difference as either plus or minus pi by 2 and same amplitude. That let us take once again, E naught 1 is equals to E naught 2. That way I am considering the same amplitude and this phi is equals to clearly pi by 2. Now what happens to the equations? Take this Ex of z. So Ex of z is equals to, as it is I can write E naught 1 cos omega t Ax, and Ey of z can be written as that directly, instead of E naught 2 I can write E naught 1 cos omega t plus or minus pi by 2 Ay. So these are the equations that what we have. Once again, we have two subconditions, that omega t plus pi by 2, omega t minus pi by 2. By considering those two subconditions, same as our previous one, I will compare them. So take this equation. Initially at plus pi by 2, omega t is equals to plus pi by, or phi is equals to plus pi by 2, I am considering Ex of z is equals to E naught 1 cos omega t Ax, and here I am considering plus pi by 2, therefore Ey of z is equals to E naught 1 cos omega t plus pi by 2 Ay. Cos omega t plus pi by 2 is minus sin omega t, right? E naught 1, a negative sign will be added, sin omega t Ay. So this is for plus pi by 2 case. In the same way, for minus pi by 2 case, just write down the equation of Ex of z. So Ex of z is same as our previous one, that is E naught 1 cos omega t Ax, and Ey of z is equals to, what is the equation? Same, E naught 1 cos omega t minus pi by 2 Ay. Cos omega t minus pi by 2 Ay is nothing but sin omega t. So which is equals to E naught 1 sin omega t Ay. So here what we have to do is just we have to observe the resultant of these two equations again. So what will be the resultant of this Ex and Ey? What will be the resultant of this Ex and Ey? And clearly observe, Ex of z is equals to E naught 1 cos omega t Ax, Ey of z is equals to minus E naught 1 sin omega t Ay. Just consider the amplitudes, don't take any vector terms, and try to get the resultant. That cos square omega t from this particular term, sin square omega t from this particular term, and add them. If we add cos square omega t and sin square omega t, what we will get? So the addition of cos square omega t is nothing but ex of z divided by E01 whole square plus. So from this particular one, cos square omega t I wrote here, and from this one write down the sin square omega t, which is equals to Ey of z divided by minus E01 whole square, which is equals to 1. Cos square omega t plus sin square omega t is equals to 1. And here clearly write down the similar type of equation here also, that is Ex of z divided by E01 whole square cos square omega t plus sin square omega t, that is Ey of z divided by E01 whole square, which is equals to 1. Right? Now if you simplify this equation, Ex square of z plus Ey square of z is equals to E01 square. Here also it is Ex square of z plus Ey square of z is equals to E01 square. Just recollect the circle equation, basic circle equation with center 0, 0 and some radius r. X square plus y square is equals to r square. Here x square plus y square is equals to r square. X square plus y square is equals to r square. So what you can interpret from these two equations? Clearly they are same, and that will gives us a resultant as a circle. Once again, same as our previous one, this circle may takes rotation in clockwise direction or anti-clockwise direction. That what we have to interpret by substituting the some initial time and final time. For that what I do is, I will take initial time and final time for these two expressions, initial time and final time for these two expressions. So what I do is, just I will consider the initial time as 0 and final time as pi by 2, same as our previous one, that at t is equals to 0, at t is equals to 0, what is Ex of z? That what I observe. Ex of z is equals to, at a time t is equals to 0 means omega t is also equals to 0. That what I do is, I will consider omega t. So at omega t is equals to 0, Ex of z is equals to E01 into 1, just it is E01. In the same way, at omega t is equals to 0, what is Ey of z? Ey of z is equals to omega t is 0. If you substitute here, the entire time is 0. Now clearly observe, initially the total electric field, the resultant is along x direction only. That at initial stage, the resultant is along x direction. Right? Now, yet omega t is equals to some random value, a positive value, pi by 2. That what I am doing is, I am increasing the time. At omega t is equals to pi by 2. What is Ex of z? So Ex of z is equals to, if you substitute pi by 2 here, then what we get is entire term 0, and Ey of z is equals to, if you substitute pi by 2 here, then what we get is 1. So the entire time is minus E01, minus E01. Now if you want to draw the graph between these two, just you take Ex on x axis, Ey on y axis, and try to draw the graph. So what I am doing is, just I am drawing graph between these two. That consider this is Ex, Ey, and this is minus Ey. At a time t is equals to 0, initially where the electric field is, the electric field is along x axis with some amplitude. Right? Later, after some time, the electric field is on y axis with same amplitude. The amplitude is not varying here. Right? So the electric field after some time is on negative y axis with same amplitude like this. Right? After some time, we can expect the same amplitude on positive y axis. So clearly the rotation is taking from x to negative y, and like this from y to x. So clearly what is the rotation direction? Y to x. Since the rotation is from y to x, it is a left-handed. So this particular polarization is called as left-handed circularly polarized signal. So left-handed circularly polarized signal always takes a rotation from y to x, and clearly it forms a circle. A similar fashion that we will examine here also. If we examine here, the rotation is always from x to y. If the rotation is from x to y, clearly we can say that it is a right-handed circularly polarized signal. Since it is a right-handed circularly polarized signal, at initial time the electric field is along x-axis, and at the final time the electric field is along y-axis. It is not on negative y-axis, it is on y-axis. So the rotation is always in anti-clockwise direction. So you can go for the similar type of analysis by considering two different times. At time t is equals to 0, what is Ex and Ey? At a time t is equals to pi by 2, what is Ex and Ey? You can take and just you draw the graph, right? So this is clearly in the left-handed direction, it is left-handed circularly polarized signal, and this one is a right-handed circularly polarized signal. So in the examination, the similar type of notation may be followed: LHCP or HCP, right-handed circularly polarized, x to y the rotation, left-handed circularly polarized, y to x the rotation will be taken place. So what we do is, just at a glance we will try to write down all the conditions for different types of polarizations. When we will get linearly polarized, when we will get circularly polarized, when we will get elliptically polarized, as a tabular form. The table will be very much useful for us. Now just at a glance we will observe what are different conditions which are required for all the types of polarizations. We will start with the linearly polarized signal. As we observed, for a linearly polarized signal the amplitude may be anything. If we have same amplitude, the polarization angle is 45 degrees, and if you have any other amplitude, the polarization angle may be vary, right? So clearly the amplitude for linearly polarized signal is anything. That just simply remember that for any amplitude we will get a linearly polarized signal. But what about the phase? The phase difference must be always equals to 0, right? The same phase you have to remember like this. The phase must be same for Ex and Ey. Here the comparison table will always gives us the comparison between Ex and Ey, right? So for that, just remember like this: Ex and Ey, for Ex and Ey, right? Now for a linearly polarized signal, the amplitude is anything, but the phase must be same for Ex and Ey. Then it is said to be a linearly polarized signal. So if we have only x component, horizontally polarized signal; if we have only y component, then it is said to be a vertically polarized signal. Now come to the elliptically polarized signal. So elliptically polarized signal, so what about the amplitude? Here we are not taking same amplitude. The amplitude may be anything once again. So clearly the amplitude may be any. But what about the phase? The phase difference must be strictly equals to pi by 2, right? So the phase difference, that what we have is, the phase is pi by 2 different. That between Ex and Ey, the phase is pi by 2 different. In that one also, if it is plus pi by 2, then clearly what you are supposed to say is right-handed elliptically polarized signal. It's a left-handed elliptically polarized, it's not right, left-handed elliptically polarized signal. If it is minus pi by 2, then it is right-handed elliptically polarized signal, right? This is a simple condition what you are supposed to remember for an elliptical polarization. Similarly, so for circularly polarized signal, what about the amplitude? The amplitude must be same, right? So the amplitude is same, remember like this. For same amplitude and phase difference of pi by 2, we are getting a circularly polarized signal. So the same condition here you are supposed to write. So the phase is pi by 2 different, and in that one also, if it is plus pi by 2, then it is left-handed circularly polarized signal. If it is minus pi by 2, it is right-handed circularly polarized signal, right? In the left-handed circularly polarized signal, Ex lags Ey. In the right-handed polarized signal, Ex leads Ey, whether it is circularly or elliptically. Left-handed lags, so right-handed leads. Ex leads Ey, so that what you have to remember. So this is a simple comparison table. With this comparison table, quickly you can answer or quickly you can observe what is the type of signal we are getting. So just by observing Ex and Ey components in a particular equation, if the amplitude is same but the phase difference is plus pi by 2, then simply you can say that it is a circularly polarized signal with left-handed rotation. Like that we have to answer the theoretical questions whenever it is given in our examination. So, with this one, the polarization for electromagnetic wave, that what we have discussed is only 3 types: a linear, circular and elliptical was almost all completed. Now, we will go for another topic or another phenomena in the same wave propagation called as reflection and refraction of the wave.